Hello, and welcome to SETI Live. I'm your host, Beth Johnson, Communications Specialist here at the SETI Institute. Welcome to our viewers from around the world. Thank you so much for joining us. Please let us know where you're watching from. Also, welcome to listeners on the podcast version of SETI Live, available on most podcast platforms. Before we get too far into things today, we have another giveaway. We have been gifted with several copies of the SETI board game. Click the link in chat or go to the link on screen to enter. This week's winner will be notified during next week's live stream. Last week's winner was, drumroll everybody, Peter Rasenberg. Peter, if you're watching, please watch your email for further instructions, and congratulations. And now, on with the show. Today, we're talking about some of the hottest worlds in the universe. Literally, they are rocky exoplanets so close to their stars that their surfaces are oceans of molten rock. Joining me is Dr. Charles-Édouard Boukaré, a planetary scientist whose new work explores how these fiery worlds form and evolve. Charles-Édouard, thank you so much for being here.
Hello, everyone. Thank you so much, Beth, for the invitation and for having me today. Really happy to talk. I'm always happy to talk about rocky planets, especially molten lava planets.
It's an exciting topic for me too. I love exoplanets and I love volcanoes. So this is kind of just like, yeah,
That's
put the two together. So let's start with the fundamentals. For people who may not know some of the terms, what exactly is a molten rocky exoplanet, and how is it different from, say, a planet here in our solar system like Earth or Venus?
It's an excellent question because actually this definition maybe is currently changing a little bit. So we used to call like lava planets or magma oceans. We used to use these words to actually define the very early stages of rocky planets in our solar system. So we believe that planets formed really hot, and so they were so hot that they were mostly molten. So the entire rocky part of the planets, we believe in our solar system was molten in the very early stages of those planets, and eventually planets cooled and so solidified, and you end up with rocky planets in our solar system that are mostly solid. But now we observe what we call lava planets. We use these lava planets to refer to another beast. This would be rocky exoplanets that would orbit extremely close to their star, so that the radiation that comes from the star will maintain the surface of those planets really hot and molten. So in that case, just the surface of the planet is supposed to be molten, but this is supposed to be a steady state. So this is supposed to be a structure that can be maintained on a billion years time scales. So let's say that in a nutshell, we can call lava planets or molten rocky planets any planets that can maintain or have liquid rocks, so lava, in their interior.
Okay, so in their interior.
So now it comes to we can start to discuss the research that have been done on lava planets. We used to think that those planets, those lava planets, were mostly old. So it was just the radiation that comes from the stars that can maintain a shallow magma ocean. And so recently, we are now considering other cases where those lava exoplanets can be actually hot for some of the reasons that we're going to probably discuss today, so that now the interior of those rocky worlds might be also molten. So we are not talking anymore about just a shallow magma ocean, but maybe the interior can be also entirely molten. So this is what we are currently interested in, and hopefully we will be able in the future with observation to constrain whether the interior is actually molten or if we just have a shallow magma ocean.
Okay, let's kind of go back a little bit here. Do we know of specific examples of these lava worlds? I know we're going to get to your paper, but did we know about them before? And if so, how common did we think they were in the galaxy?
So I think the first observation dates back from the early 2000s,
Okay.
and it was mostly based on two arguments. They found a planet that orbits really close to the star with a density that is consistent with the density of a rocky world. So
Okay.
not assume Neptune or odd Jupiter. So we are really talking about rocky planets. And then by doing quick calculations, you can show that if the rocky planet is at close, at the surface, the stellar flux must melt the rocks at the surface of the planet. Something important that we can introduce that we're going to use in our discussion is that those exoplanets, so now we are talking about the exoplanets, not the lava world in our solar system, they orbit so close to the star that they are tidally locked by tidal forces. So it's actually the same face, the same hemisphere that faces the sun all the time. So this is what we call the hot side or the day side of the lava planet, and it is this day side that is mostly molten. So
I feel like day side is being nice.
yeah.
So yeah, there's a lot of sunlight, but that doesn't make it livable.
No, you don't want to live there. You don't want to live there. So we are talking about, actually we should put numbers here. We are talking about surface temperatures around 2000 kelvins.
Wow.
That can go up to 4000 kelvins.
Oh
And
my
the
gosh.
melting temperature of rocks is about 1500. So you can not only melt those rocks, but also vaporize those rocks. So this is also something that is extremely interesting for us, if that actually we are the atmosphere that we expect on the day side of those exoplanets are atmospheres made of rocks. So I know it's weird to visualize, what would this atmosphere look like? But yes, at those temperature, rocks are in the vapor state.
That's wild.
And so to go back to your question, how common are the subjects? We know there is a dozens of those, because since they actually orbit very close to their star, they are very easy to detect. Also, we can put some numbers here. We are talking about orbital periods of few hours up to 24, 30 hours. So 1 year for those exoplanets is about 1 day on Earth.
Wow. So moving along really quickly as well.
Yes.
So these are not habitable worlds, everybody.
No.
All right.
Don't want to live there.
So let's get into your paper, but first let me remind everybody we are giving away the SETI board game. We gave one away last week. We're giving one away this week, so make sure you go to that link above me and enter to win. So very exciting. It is definitely a European style board game. So if you're into that kind of thing, highly recommend. Okay. And also, welcome into our viewers. So far, I see people watching from Brazil, from here in California, and from Sweden. So definitely got a bit of a mix. All right. Charles-Édouard, can you walk us through the main findings of the study? What did you discover about magma oceans and planetary interiors?
So in this specific paper, I would say there are like two main findings. The first one is that we show that we can hope to observe lava exoplanets that would be mostly molten in the interior, so very hot. The second thing is that we showed that somehow the depth extent of this lava, of this magma ocean, so the thickness, if you want, of this magma ocean, of the amount of lava that you have, should correlate with the composition of the atmosphere, the mineral atmosphere on the day side.
Okay.
And so this offers a way to actually constrain a bit better those exoplanets. So somehow we predicted that if the exoplanet just has a shallow magma ocean, the atmospheric composition should look like this at first order. But if the magma ocean is global and you have a lot of liquids, then the atmosphere should be different.
Okay.
How did we do this? We coupled the fluid mechanics of the motion in the magma. So imagine it's like, water, the water ocean on Earth. We have, water circulation, water moves in some directions. So you need to increase the thickness of this water ocean significantly, so that actually could cover the entire part of the mantle.
Mm-hmm.
And you couple this with the chemistry of melting and solidification. What was not explored before was the complex interaction between fluid motion and chemistry. And it's especially important in this case because, remember, on the day side, everything is hot and molten.
Mm-hmm.
But on the night side, everything is cold and solid. And the thing is that you're going to have fluid motion that's going to bring materials from the hot side to the night side.
Mm-hmm.
Then materials will solidify, get entrained into the global circulation, and then go back to the day side. Why do we want to model the chemistry there? Maybe you know that all elements do not behave the same when
Mm-hmm.
it comes to melting. Some elements want to stay in the liquid. We say that they partition into the liquid and the magma, and others stay in the solids.
Mm-hmm.
So the fact that we have this global circulation, where on one end you're going to have magma in the liquid state, and on the other side, the night side, you're going to have magma in the solid state, so rocks. It's a way to actually distillate the planet, and this would drive the chemical evolution of the magma ocean progressively, because all elements will stay, elements that prefer to stay in the liquid, they will stay in the liquid. And we show
so this could be as complex as some of the magmas that we see here on Earth, where
Absolutely.
we have those very like young pristine magmas, and then we have the more complicated melted older rocks kind of thing. So correct?
Absolutely, that's exactly that. So what we are doing is just extending and pushing the limits of this concept to the extreme, where actually it's an entire planet that is molten and that is constantly solidifying and remelting. But the concepts are exactly the same.
Okay, that makes sense. I am losing my terminology for magmas, and I should have them, but okay. I'm going to welcome in one more person from the south of France. Bonjour. Let's zoom out. Well, okay. You were kind of talking about the interaction between the mantle and the atmosphere. So how does this work? How does the interior and the atmosphere interact? Is there anything else we need to know about how this operates with this particular world or these worlds in general?
No, it's really, there are a few things that we can mention. So first, maybe I can say a few more words about this mineral atmosphere,
Mm-hmm.
and maybe how it could be distinguished from maybe a more volatile atmosphere, so the more let's say the classical atmosphere that we are used to, so made of CO2, water vapor, etc. Because you can have both actually on those exoplanets. But the most important thing is that no matter what you do, the magma ocean must be in equilibrium with the atmosphere. So what you have in the magma ocean will dictate what you're going to have in the atmosphere. So you, on the day side, where it's hot enough so that you can vaporize those minerals.
Right.
And part of this study that we did is to show that if the composition of the magma ocean changes, the composition of the atmosphere in equilibrium should also change and reflect those changes.
Makes sense.
And Based on this research, we propose that maybe in the future, if we can measure the composition of the atmosphere with good enough accuracy, we can retrieve what was the composition of the magma ocean. It turned out that it would be quite challenging to reach the good signal to noise ratio, but maybe with future telescope like the ELT, this is something that we could do. But it's not something that we should expect to be able to do with the James Webb Space Telescope, for instance.
That's too bad, because it's really cleaning up the floor with the atmospheres of exoplanets. All right.
Yeah.
I want to zoom back out a bit, but once again, welcome to people watching from Scotland and Poland. So definitely, again, a nice global audience today. And a reminder, board game, free board game. Go to link. It's up here and it's in the comments on several of our platforms, and you can enter to win a board game. And we will announce that next week. So let's zoom out. What can studying such an extreme planet, because it is an extreme planet, it's very interesting. I find it amazing that in all of the very few years of knowing that we have exoplanets and things having to be, that we've confirmed them, now it's like, oh, we found an exoplanet, no one cares. We found a really weird exoplanet, yeah, everybody cares. So I think that's amazing that the science has gone from this very broad to very narrow, let's find the wildest things we can find. So that's where we're at with exoplanet research, really. But what can studying extreme planets like this teach us about how rocky planets evolve, say, in general?
Very good question. I like this question. I would say this kind of study could help two kinds of discussions. The first one would be the composition of a planet.
Mm-hmm.
So as you may know, right now, it's really difficult to actually have a relative accurate description of the composition of rocky planets interior. We basically say, oh, there are either hot Jupiters, sub-Neptunes, rocky planets, and that's it.
Mm-hmm.
But maybe in the future, we want to be able to distinguish Mercury from Earth, for instance,
right.
or Mercury from Mars-like planets, because we know within the solar system that those slight differences have major implications on the long-term evolution of those objects. So these kind of models where we offer avenue to connect the composition of the atmosphere that we can detect, well, again, in the future, we hope that we'll be able to detect those. With the one of the interior, this will then offer a way to probe the actual composition of the interior. And instead of saying just, oh, this is a rocky planet, we can say, oh, it's a rocky planet with this amount of magnesium, this amount of iron, this amount of calcium. And yeah, this would improve significantly or the level of description that we can have for those exoplanets. Another aspect that actually I have discovered when doing this research would be more related to the mechanism of planet formation.
Yeah.
As you may know, all those exoplanets that we find, they are challenging significantly the way we believe planet formed. In our solar system, there is no, giant planets that orbit very close to stars. There is no lot of sub-Neptunes. So we need to revisit how planet form. One aspect of planet formation would be planetary migration. During planet formation, our planet can migrate, so maybe they can form at a given location in a protoplanetary disk and then move. And I believe this is something that we need to improve in our model of planet formation, and exoplanet research can help us a lot about this. So to go back to this research, by actually probing the thermal state of a lava planet. So I talked about the composition, things that we are at the limit of being able to do with James Webb. But I haven't talked about the fact that we can actually probe the night side temperature measure the night side of the temperature of those exoplanets with James Webb. This is something that we can do. By measuring the night side temperature of those planets, we can then retrieve their interior temperature. This was another aspect of this research. And by retrieving the interior temperature, we can actually offer constraint on the, at first order, on the thermal evolution of those planets. So, and now this can be related to the migration history of those planets. I can give you a more practical example. We expect, so actually this study goes with we have been lucky to have been awarded observation time with James Webb to actually test our hypothesis.
Congratulations.
Thank you, thank you. And so the idea that we propose is to observe, to measure the night side temperature of five different exoplanets. Some of them we know they are young, others we know they are old. And so at first order, we expect that old lava planets should have a cold night side surface.
Okay.
Because they are old.
Right.
But if there is more complexity in their migration goes with tidal dissipation, tidal heating that can maintain actually a hot interior.
Right, okay.
So what I'm extremely excited about would be to find a very old lava planet that is actually hot and fully molten inside. That would mean that the migration history is maybe a bit more complicated than what we think. And this would be a way to maybe connect this to the big picture of planet migration and planet formation.
You just want planetary formation to be more complicated. Like it wasn't complicated enough. That's the flip side of discovering all of these exoplanets is that we went from one example of what a solar system looks like to us to thousands, we're up at like 6,000 exoplanets now. And we've had now a very different perspective on planetary formation because things don't make sense for what we have based on what is out there. So it has definitely been very wild. And I have said this for years. I don't know that we will ever really solve planetary formation because there's so many complexities to it and so many moving pieces. But I do appreciate that you want some more complexity. I'm here for this. So we're getting some audience questions in, and I do want to address some of them because there's some good ones out there, and they kind of go along with what I wanted to ask anyway. So as
Excellent.
a reminder, enter for the board game up top. Again, European style SETI board game. It's based on real SETI science. The designers checked in with us and wanted to make sure that it was fairly accurate, and so we have played it, and it is complicated but fun. So go for that, and we will ship it to you. And believe me, when you get it, you will be like, oh my gosh, this box is huge and heavy. Okay, so let's look at some of these audience questions. Ron Schneider, who is one of my regulars here, and I really do appreciate that you show up for every stream, Ron, has questions about basically the population of lava planets in general. And so you said like you're going to observe 5 with James Webb for one particular feature. What can we kind of say about some of these lava planets? Can we talk about like how they're formed? Do they have to be tidally locked? Are they all one half hot and one half cold so far from what you found? All of these are Ron's questions, and they're all really good sort of general population questions for this.
Yes, we believe that. Let me think what would be the best way to answer that question. It's a very good one. I'm going to answer this question with what I believe is the most interesting hypothesis. Lava planets can't form at their current location, so the location where we observe them.
Okay.
It's way too hot, so that means that they come from probably far away. They migrated inwards. Some are currently postulating this hypothesis that this actually could be just the core of sub-Neptunes that just lost their hydrogen and helium envelopes.
Okay.
So that means you start with some kind of sub-Neptunes or something bigger. This migrates inward, and then you get blasted by the star, and you lose the atmosphere. And what remains is just the silicate cores that looks like a rocky planet, but actually is just sub-Neptunes that has been desiccated.
Which also goes towards solving one of our sub-Neptune problems in
exactly.
that we're not finding the examples in a certain range, and we do think that this is what's happened, is that in that range is where that atmosphere is getting sort of blown off by heat. So, okay.
Exactly. And then, so what are the main variable parameters that lead to a planet to become a lava planet? Yes. So I believe I somewhat answered that question already, I hope.
So, and then again, back to do they have to be tidally locked? Does that seem to be one of the criteria at this point?
Good question. Yes, actually, it seems that it has to be locked due to the very close proximity to the sun.
Mm-hmm.
Tidal forces are so large that this tidal locking will actually occur on a very short time scales. So yes, we do not have reason to say that there cannot be tidally locked. Some details that I have seen is that if you have a slightly eccentric orbit,
Mm-hmm.
even though if you are tidally locked, the day side, the surface area of the day side can change slightly. So in that case, you do not have a very perfectly static day side.
Right.
But still, you need this tidal locking.
And that's true of our moon. Like our moon is tidally locked, but
Absolutely.
it has a slightly eccentric orbit where it does come closer and further away. And so over the course of a lunar month, you can actually see this shift in what you see of the face of the moon. So that makes sense. Okay, so they have to be tidally locked. Now, that you did bring up you mentioned tidal forces, and this is a question I'm so feeling silly that I didn't think to ask this, but Yellow Gorse is asking, could a lava planet have like tides, like regular tides, like the moon causes here?
Yes,
now I want to think about like magma, lava oceans like coming in and going out with the tide. Like I'm all having this vision. So
I don't think it would look like tides on Earth that are driven by the motion of the moon, because so everything gets confusing here. The moon is tidally locked,
right.
But the tides that we are experiencing on Earth when we go to the sea, of course, happens at the surface of the Earth. So on those objects, those lava planets play the same role as the moon.
So they would more likely cause a pull on the star itself.
Exactly.
Okay.
But,
yeah, all right.
Yeah.
That makes sense.
But actually, this is something that I'm actually currently learning. You can have both tidal dissipation in the star and in the exoplanet as well. And depending on the orbital dynamics, the detail of the orbital dynamics, sometimes you're going to have more tidal dissipation within the star, sometimes more within the planet.
Oh, God. Oh, this is so cool. Or so hot. I mean, All right. So what's next for you? What are you going to be working on? You mentioned that you have some JWST observations to be taken. Obviously, you're not going to be doing ELT observations anytime soon because we still need to finish building that. But what are you working on now? What's next for Charles-Édouard?
So for regarding this project, of course, I would like to see the data. So it seems that we should get those data in spring next year. And we'll see. Again, my hope, really my hope is to observe an exoplanet that is old but hot.
Yes.
If we can find one of these, then I think I might start to learn a bit more about orbital dynamics, migration, the coupling between orbital dynamics and the time and state of planets to maybe connect a bit more those two. So this would be something I believe important for better understanding the evolution of the subject. The other aspect would be to improve the link between, to maybe improve a bit the chemistry in those models. Try to see if we can do better, try to see if we can match the sensitivity of James Webb, if there is a specific species that we can maybe observe easier than others. This would be a second line of research. Another one would be also to learn more about subneptunes. How can understanding of magma ocean can help our understanding of subneptunes? As you may know, we believe that maybe there is actually a magma ocean below the let's say the atmosphere of subneptunes, and the same thing that we were discussing. So the chemical equilibrium between the magma ocean and the mineral atmosphere on lava planets. The same concept would apply on subneptunes, except that the thickness of the light atmosphere that you have is so large that the magma ocean would be at extremely high pressure. So it will be a very pressurized magma ocean. But same thing, that would dictate the composition of the atmosphere of subneptunes. So this is also something that I'm getting more and more interested in. Yeah, let's see what we can do in the future.
This has been very exciting. This has been such a fascinating look at these extreme planets, and I am so thankful, Charles-Édouard, that you came in and joined us and shared your work. So thank you so much for being here.
Thank you. It was a pleasure. It was a pleasure.
Thank you to everybody for watching. The link to the press release is in our show notes down below. You can also find the link to the Nature paper, and if you have access to that, you can take a look at it. If you enjoyed the conversation, please like it, share it with your fellow space nerds, subscribe on YouTube for more space science interviews like this one. Next week, Frank will be back, and he will be speaking with Martin Dominique, one of the authors of a recent white paper that examines the societal, political, and philosophical challenges we'll face once, when, not if, alien life is confirmed. So stay tuned. Don't forget to enter our giveaway. Come to our website. You can subscribe to our newsletter and hear more about all of these different talks and get links to all of them coming up and to all of the ones in the past in case you missed one. And also, we are for a 501c3 nonprofit. So all of your bits, subs, stickers, super chats, all of those things go to supporting this program and keeping us being able to bring fantastic scientists like Charles-Édouard here to our show. And so if you feel generous and you have the ability to help, just hit that donate now button and jump on in. So until next time, everybody, keep looking up and stay curious.